You're welcome to Exam Scholar channel. If this is your first time of coming across our channel, kindly subscribe to this channel. So if you haven't watched our previous video in which I explain wave types of wave and properties of wave, progressive wave, please make sure you watch the previous video, as this video is a continuation of wave. Now, what are we learning in this video? We are learning sound waves. So we're going to quickly look at the meaning of sound wave, how sound wave can be generated, and how it can be propagated. So make sure you subscribe to this channel and click on the notification icon to get more videos. All right, without further ado, let's start the class. So when we talk about sound wave, we need to understand sound energy before we can now understand sound wave. Right, sound energy is an energy produced by vibration of bodies. So if you want to hear sound energy, just look for vibration. Whenever there is vibration, sound always accompanying vibration. Let me give you a practical example so that you understand what I'm saying. Now, just clap your hands. As you are clapping your hands are moving, vibrating, therefore sound will be produced. When you beat the membrane of drum, the membrane will vibrate, sound energy will be produced. Okay, now just observe in your room when you switch on the fan. As the fan is rotating, you are going to be hearing some sound due to the vibration. If the blade of the fan is not balanced and the fan is rotating, vibration is going to set in, and that vibration will lead to noise. You'll be hearing some funny sound. You'll be hearing some funny sound. Now, as I'm speaking, all my vocal organs, they are vibrating, and that is producing sound. Okay, now the vibrating bodies will now cause the surrounding particles to vibrate, passing energy along from particles to particles. So this is how sound wave is being generated. Don't forget that wave is what? Energy carrier, disturbance that moves from one point to the other point. Now, as vibration is now happening, the surrounding particles will also receive energy, thereby transferring the sound energy from one point to the other. So this is what leads to sound waves. Now, don't forget that sound wave is an example of mechanical wave that requires a material medium for its propagation. So when sound is going to be propagated, move from one point to the other by what we call sound wave, we are going to need a material medium, be it solid medium, liquid medium, or gas medium. Now, let's quickly observe the pattern of production of sound wave. Now, sound wave basically is produced by the rarefaction and compression of the surrounding medium. So when something is vibrating, the rarefaction and compression of what is surrounding it will lead to sound waves. Now, as I've showed in the animation, now look at this very well. You see that there is a point at which all these rings, they clog together. They are compact. The distance between them is not much. This is what we call high pressure region. And high pressure region is what we call compression region. Compression region. So which means that the particles are clogging together. The surrounding particles are clogging together due to the vibration of this membrane. Let's just assume this is a drum. So this is the region that is known as compression region. We also have the other region which is known as rarefaction region. Now, rarefaction is a low pressure region in which the surrounding particles, the distance between them is larger compared to this epicenter, the compression region. So if someone is now asking you, how is sound wave being produced? Tell the person sound wave is produced by vibration, which leads to rarefaction and compression of surrounding medium. So that is how sound wave is being generated. Don't forget that sound travel faster in solid medium compared to liquid medium, then compared to gaseous medium. Now to the properties of sound wave. Sound wave can be reflected like every other waves. It can be refracted like every other waves. It can be diffracted, and it can also interfere. Sound wave cannot be polarized because it is not a transverse wave and it is not an electromagnetic wave. Alright, let's quickly look at reflection of sound wave. Now, reflection of sound wave occurs when sound is traveling in medium and it encounters a strong surface, a hard surface, thereby it changes direction. So that is what is known as reflection of sound wave. So reflection of sound occurs when sound is moving in medium and it encounters a hard surface, thereby changing direction, moving back, reversing its direction. So that is what is known as reflection of sound. Now let's have this diagram. Let's have this surface, a hard surface, and let's generate some sound wave. And let's see what will happen as the sound wave hits this hard surface. Now you see that it reverses its direction. That is what is known as reflection of sound wave. There is a phenomenon that is known as reflection of sound, which we are going to learn. Sound wave can also be refracted, so which means it can change its direction or bend, or it changes its speed as it moves from one medium into the other medium. So sound wave can also be refracted. It can also spread out, which is known as diffraction. Sound wave can be diffracted, can spread out. If someone is speaking outside your house and at one corner of your house, then you'll be able to hear the sound due to the diffraction or spreading out of sound in your room, and that is possible due to the diffraction of sound wave. Sound wave can also interfere, so which means that multiple sound waves can come together to produce a louder sound wave, higher amplitude, and they can also cancel out each other. So that is that for sound wave. We want to observe what is known as echo in the reflection of sound wave. So if someone is asking you what is echo, now echo is a sound that is being heard after a sound reflected on a hard surface. When a sound is produced and then you're able to hear the sound back after few seconds or some microseconds, that is what is known as echo, because the sound has reflected when it hits a hard surface and you were able to hear back the sound. That is what is known as echo. Echo. Now there's another phenomenon that is known as reverberation. Reverberation. Now reverberation is multiple echoes. So when sound is being produced and sound wave is being reflected at multiple times, that is what we call reverberation. To learn this, let me quickly give you a practical example. Reverberation. Now that is a practical example of echo. The first one is echo. The second one is reverberation. Now there is one calculation that we usually solve in reflection of sound. It will give you where we can apply the knowledge of reflection of sound. In the exploration and mining, sound reflection can be used to determine if there is a hard rock in the ground. Let's say, for instance, you want to drill a particular spot and you want to check if there is water. Some sound signal, sound wave will be sent into the ground, and then they are going to observe if there will be reflection of the sound wave using some special instruments. So once there is reflection, they can predict that, come on, there is a hard rock in the ground, and when we penetrate this hard rock is going to give us water. Another one is, if you want to know the depths of ocean, we can also apply the knowledge of sound wave. It's very simple. You are in the ship and some signal is going to be sent. Sound wave is going to be sent down into the ocean, and then they are going to wait for some time when this sound wave is going to be added back. It's going to be reflected. Now recall that sound wave is going to be reflected when it hits a hard surface. So when the sound wave is now traveling down to the depth of the ocean, to the floor ocean, then it will now reflect back. They calculate the time taken, and don't forget that sound has speed. There is a speed for sound in the water, there is a speed of sound in the air. Now, having understand the speed of sound in the water, they will now use that analysis. They have the speed of sound in the water, they have the time taken for the sound to be added back. They can now use the analysis, the calculation that I want to show you to calculate the depth of the sea or ocean. Now, let's say this is a drum and this is a wall, a hard surface. And sound wave is being produced by this drum, which means sound is produced by this drum. And then we struck this and sound wave hits this surface and it's going to be reflected back. Now observe something here. There is a distance between this source and this wall reflecting surface. Let's call that distance S. Now recall that speed of sound, or speed, generally speed is equals to distance over time, or velocity is equals to displacement over time. Okay, now this sound that is produced is going to have speed, isn't it? Okay, which is constant for medium. Okay, depending on the density of the medium. Now, as this sound wave is traveling, it travels from here to here. It covers some certain distance, S. It's reflected back again, cover the same distance, S. So which means two distances being covered. And all this thing is happening at instance of time. So we can take time measurement. Okay, now let's plug in those values inside our formula. Now we know that distance is equals to speed times time. Then you have 2s is equals to v multiplied by t, the velocity times time. And what will now be the distance? The distance will now be equals to what? V times t over 2 when you divide both sides by 2. So you can use this expression to find the distance between the source that is producing sound and the reflecting surface, when you can measure the time at which you add back the echo. So now you can use this formula to quickly find the distance between the reflecting surface of sound and the source that is producing it, provided that you can measure the time taken for you to hear back the echo, when you can add back the echo. So you use this formula to solve question. Now let's solve this echo question. A boy received the echo of his clap reflected by a nearby cliff 0.8 seconds later. How far is it from the cliff, given that the speed of sound in air is equals to 340 meters per second? So you are given this speed. How do you solve this question very fast? Now recall from my previous explanation that distance is equals to c times t. Speed times time, we all know this. Speed times time will give you distance, Abi. And if you look at the explanation, I explained to you that the distance, the movement of that sound will be in two directions, to and fro. So which means 2s is equals to speed of sound multiplied by time. What will now be s? S is equals to c times t over 2. Oh yeah, just plug in your value. So what is the speed given in the question? 340. What is the time taken? 0.8 divided by 2, 272 divided by 2, and you have 136 meter. Intrinsic properties of sound wave. So we want to look at sound generally. There are some phenomena and properties that is meant for sound. Let's quickly look at them. Sound frequency, relationship between sound frequency, pitch, and octave. Recall, their frequency is the number of oscillation made per second. Oscillation per second. Okay? Now, when we talk about pitch is just like a perception of how high a sound is or how low a sound is. Pitch is different from loudness of sound. Take note. Pitch is the perception of how sound is high or how sound is low. Okay, it's just a perception of sound being high and sound being low. Now, you now see this pitch. It depends on the sound frequency. When the frequency of sound is high, the pitch of that sound will be high. When the frequency of sound is low, the pitch of that sound will be low. Don't forget that pitch is the what? Perception of how sound is high or how sound is low. The higher the frequency, the higher the pitch. Or the higher the pitch, the higher the frequency of sound. The higher the frequency of sound, the higher the pitch of sound. The lower the frequency of sound, the lower the pitch of sound. The lower the pitch of sound, the lower the frequency. Don't miss this. So pitch depends on frequency. Let's look at the practical example of pitch. Let's look at our voice, for instance. Let's look at our voice. Now you see that my voice is very thick. You can observe that my voice is very thick. Now, this is a low pitch voice. A very low pitch voice. This is a man voice. A baritone voice. Now, generally, man used to have a very low voice. We have a what? A low pitch. Now, let's look at choir. In choir. Yeah, let me change the mood of this lecture. Let me switch. Okay? Now, let's look at, for instance, choir. Now, you observe that we have baritone singers, we have bass singer, we have treble singers, soprano singers, alto singers as well in church choir. Okay? Now, you observe that the one that are singing bass, and when you look at them, you see that mostly they are males. 90% of them, they are males. Naturally, male has a low pitch voice. But we still have some male that have high pitch voice. Okay? Now, male, we have a kind of voice that is oxkey. We call it oxkey voice. So that is low pitch, low frequency. Now, when it comes to female, they have a light, high frequency voice. So they are soprano singers. You find female in soprano singers. 90% of them, they are soprano singers. When you look at soprano singers, you see that 90% of them are females. Because the voice of female is very tiny. That is high pitch. High pitch. Now let's look at this octave. And for some of you that you know how to play instruments, well done, you will understand what I'm saying. You understand it better. Now, for octave is when you are doubling or when you are halving the frequency of sound. Come again. When you are what? Doubling or halving the frequency of sound. Now, high frequency leads to high pitch. Let's quickly observe something here. Now we have this diagram. This is what? Yeah, compare these two diagrams. This one is what? High frequency. This one is what? Low frequency. Okay, which leads to low pitch. Now let's quickly observe the meaning of octave. Octave. Don't forget, octave is what? Doubling or halving the sound. Higher octave means you are doubling sound. Lower octave means you are halving it. Now let's look at this sound from musical instruments. 220 Hz frequency sound, which is a 3. This is the top octave in musical instruments. We are playing piano, you are playing flute. This is a 3. This is the frequency of a 3. Okay. What is the lower octave of this? For lower octave, you start halving it, dividing it by 2. So A2 will be what? 220 divided by 2, and that is 110. A1 will be what? 110 divided by 2, and that is 55 Hz. And let's quickly look at higher octave. For higher octave, you start doubling this. Okay, the first higher octave will now be what? A4. Now A4 will be 440 Hz. A5 will be what? 880 Hz. You still don't get it, just be multiplying this by 2. When you multiply this by 2, the next one you multiply it by 2 again. A6 will be what? 1760 Hz. It's not all the sound that is audible to human ear. Now, sound range can be classified into 3. So we have infrasonic sound. These are sound that the frequency is below 20 Hz. You see this sound, human being cannot hear this sound, e.g. the communication mode of elephants. Now, elephants produce some kind of sound that are below 20 Hz. They use it for communicating, so we cannot hear such sound. Now, we have ultrasonic sound. Now, this sound, the frequency is above 20k Hz or 20,000 Hz. Now, this frequency cannot be heard. Any sound that is produced with such frequency cannot be heard by human being. So we cannot perceive or hear such sound. Now, we have some animal that can hear above such sound, e.g. the likes of dog. That is why dog is very sensitive, because dog can hear sound that the frequency is above 20k Hz. They are very sensitive to such sound. They can hear it, they can perceive it. We now have the audible range sound for human being, for human ear. The audible range for human ear is the sound between 20 Hz to 20,000 Hz. In between that range, that is what human being can hear. Now, as we grow old, the range will be coming down, so we'll be unable to hear high frequency sound. Now let's look at timbre, or timbre. I don't know how to pronounce it. Timbre. Okay, timbre. So which means sound quality. You can call it sound quality, sound uniqueness, or timbre. Okay, we want to look at timbre and overtone. When we talk about sound quality or timbre, it is the intrinsic properties of a sound that makes us to differentiate it from other sound. Now, you can have multiple sound that is having same frequency, which means same pitch. They have the same octave. On the same octave, they have the same amplitude, same loudness, but you can still distinguish them. Let's say, for instance, we have, as I'm playing those musical instruments, you should be able to differentiate the sound. Okay, this one is coming from piano. Okay, this one is coming from saxophone. Okay, this one is a violin sound. We will still differentiate it. So the quality of sound, what makes sound to be unique. Now, let's say if I sing a song and you also sing a song, if you are singing the same volume, the same key, now you will still note that, come on, this is Mr. Wale that is singing. Come on, this is this guy that is singing. So that is sound quality, the ability to distinguish between different musical instruments or different sounds. So that is sound quality. Now, sound quality is as a result of multiple overtones that is taking place in the musical instruments or what is producing the sound. Okay, you can easily identify piano compared to sax. Okay, amplitude of sound, loudness of sound, and sound intensity. Let's differentiate between them. Now, you know that amplitude is the what? Is the maximum displacement from the point of rest. Okay, now to better understand amplitude, let me show you this diagram. From here to here, this is the amplitude of the sound. Okay, Now, loudness is also a perception. Okay, a perception of sound being loud, because a sound that I might consider as being loud might not be loud when it comes to you. For instance, I hate noise, even though I'm an instrumentalist. If I'm playing musical instrument, I used to low it. It's just all this talking drummer that will be making noise. Okay, now loudness is just a perception. Now, how do we now measure loudness? Loudness is measured in decibel. Decibel, which is coming from logarithm. Okay, loudness can be measured using decibel, and the higher the amplitude of sound, the higher the loudness of sound. Now let's now look at another thing, which is sound intensity. Now sound intensity is sound power per unit area. Sound power per unit area. To understand sound intensity, let me use a practical example to understand sound intensity. So if you have ever been to a big auditorium, a big cathedral, a big church, that they have like multiple speakers will be producing sound energy, abi? Now the area inside that auditorium, which is the space, divided by the sound that is being produced, the sound energy, the area of the auditorium, you have it. Now the power of the sound that is being produced, don't forget that power is what? Energy divided by time. Okay, now when you now divide it by the area, the space, you get what is known as sound intensity. Now just carry all the speaker from big cathedral and bring them down, all the musical instruments. Now just bring it down to your room and start playing it. So which means that when you start playing it in your room, everywhere will be shaking. The intensity is so much. And that's a particular example of intensity. That's sound intensity. Power per unit area of sound. So the SI unit of sound intensity is what? What's the SI unit of power? Watt. Okay, area, meter square. So you now have watts per meter square. So intensity is also proportional to amplitude. The higher the amplitude of sound, the higher the intensity. Don't let us move further in this intensity. Let's just pause for now. You're writing UTME exam and AP exam. Now, between this sound and this sound, which one will be louder? This one, because this one is having higher amplitude than this one. Sound intensity, power per this. SI unit is watt meter square. Now let's now talk about this guy. I love this guy. Let's talk about this guy. For some of you that you are playing musical instrument, I'm going to abuse you. Just calm down. So we are going to have what is known as music or musical sound. So now we are going to have the opposite that you guys used to do. Noise. The noise, I'm the one that splits noise into two. Okay, we have musical noise and we have normal noise. Noise. Okay, let's understand what is known as music sound or musical sound. Now you can be clapping your hands and be making music with your hands. So which means that music is a well orchestrated and programmed sound. A sound that is well prepared, that is having a rhythm, a well-defined pattern, and it is repeating. That is what is known as what? Musical sound. Let me give you a practical example of musical sound. Now, I'm trying to make a pattern by creating a music, using a music style, using a music genre. Now, that is a musical sound. Now, you can use any musical instrument to form musical sound, and you can also sing, you can clap. You can use your mouth to form musical sound. You can start beating drums and be forming a well-defined pattern that will be appealing to hear, that will synchronize with the brain. The brain can easily assimilate and it can affect the brain positively. That is what we call musical sound. Music is spiritual. Now let's look at noise, which you guys used to make. Noise.
let me give you a practical example of noise. I don't even need to define noise. Just go to the market square and all the sound that you are hearing, that is noise. Now you hear a car hooting, pam pam pam. You hear a syringe, wow wow wow. You hear different type, you hear different kinds of sound that is not well defined, just coming, interference up and down. The sound, your brain cannot even interpret the sound. You are just hearing multiple different sound coming here and there, car, truck, train, people shouting, screaming, different sound. So that is noise. Okay, now let's now explain musical noise. You can use your musical instrument, what is meant to make music, and you'll be thinking that you are making music, but it is noise. It is noise. Let me give you a practical example. For some of our local church, you want to sing praise and worship, praise and worship, you carry 4 talking drummers, there's nothing bad there. 4 guitarists, there's nothing bad there. 4 keyboardists, there's nothing bad there. But you fail to have good sound engineer. Now, all these instrumentalists, they don't understand music. Most of them, they don't understand music. We have some that understand music, but we have some that they are very stubborn in our local churches. They don't understand music. Now, they will start playing musical instruments. The person that is singing will be singing. They will not start increasing the volume. Is it musical instrument that we want to hear, or we want to hear the song, or we want to hear a balanced sound? At the end of the day, everything, talking drummer, I can't hear myself. Talking drummer will now say something. Okay, come on, help me to increase the sound. Help me to increase the volume. I can't hear what I'm playing. Me ogbon continue play. Eba mi fun ni volume. Eba mi yi sókè mi ogbon. Now everywhere will now be the noise all around. God is not even happy about the sound that we are making, because it is not a unique sound. If you are privileged to get to heaven, I've not gotten to heaven, you will see that the sound that they are generating, the angels are generating in heaven, they are melodic sound that is very unique, well structured, solemn sound, unique sound, shout of praise. So that's about musical noise. You can use your keyboard. You can be singing instead of you to be making music, but you are making musical noise. You are just making noise, right? That is the meaning of musical sound, noise, and musical noise. Now let's look at musical instruments. We have different types of musical instruments. We have percussion instruments. Let me just give you the meaning of percussion instrument. You don't need to be stressing yourself. Percussion means something that you are beating, that you are beating. Any musical instrument that whenever they want to play it, they are beating it. That is percussion instrument. E.g. drums, e.g. talking drums, e.g. xylophone. All these musical instruments, they always beat them. They will beat them. So that is percussion instrument. Then we have string instrument. Now string is just like a rope, or it can be made from polymer, normal rope, or a melter that is styling, that will be fixed at both ends. That is what is known as string. Now we have some instruments that use string, e.g. violin, your guitar, your bass guitar, your lead guitar, we have many instruments like that they are string instruments. Another one is piano. I'm not talking about keyboard. The one that we are playing in church, they are keyboard. But we have piano. Piano is a string instrument. When you check it, I'm talking about mechanical piano. I'm not talking about digital one that you know as keyboard. Piano, they are string instruments. Piano is different from keyboard. Keyboard, that is a synthesized sound. A sound that is programmed. So once you press the key like this, they will have a panel under it that will process what you are playing, and it's going to bring out a digital output. I'm talking about analog piano, grand piano. That is a string instrument. Now we also have a wind instrument. You see this one, or ear instrument. For you to operate them, you just blow here. For string instrument, you just going to play the string, strike the string. Now for this one, you beat it. For this one, you strike the string. For this one, you blow it. You blow here inside it. Example: trumpets, saxophone, flute, recorder. These are wind instruments.
How can we find the speed of sound in material medium? So when you want to find the speed of sound in air, speed of sound in water, speed of sound in a solid material just like a melter, how do you find it? I'm not going to bore you with the derivation, so I'm going to go straight to the point. Now, to find the speed of sound in any material, you just need to know these two values. So speed of sound is equals to root of K divided by rho. This K is modulus of elasticity of that material medium. Okay. Now this rho is density of that material, the material medium. So let's say you want to find the speed of sound in air. What you just need to do is, if you can find the modulus of elasticity of air and the density of air. So you have root K over rho. Now, using the knowledge of thermodynamics, this one can be reduced. Now let's go. Where our C is the speed of sound, meter per second. K is the modulus of elasticity. Remember from elasticity, from Hooke's law. Okay, modulus of elasticity, the SI unit is Newton per meter square, which is still the same thing as Pascal, which is still the same thing as the SI unit of stress. Extra unit of stress is still having the same unit as stress. Okay, now rho, which is the density, the SI unit is kilogram per meter cube. Okay, now if you are not talking about air, you use this. All these things can be reduced to this using the knowledge of thermodynamics. You can reduce this to something like this for air. So which means that the speed of sound in air will now be 331.3 root 1 plus temperature of that air in degrees Celsius divided by 273.15. 273.15. C is equals to 331.3 root 1 plus T in Celsius divided by 273.15. Now this is an expression to find the speed of sound in air. So which means that the speed of sound, now look at this formula, is proportional to temperature. Okay, so we are still going to break down that formula. Can reduce what we have here. We can reduce it and find a simple expression for this. And what is that simple expression? C is equals to 331.3 plus 0.606 times T in degree Celsius. 331.3 plus 0.60 times T in degree Celsius. So you can be given a question where you are asked, what is the speed of sound in dry air at certain temperature? So what you just need is to convert that temperature to degrees Celsius and you plug in that temperature here, then you can get the speed of sound. Okay, now where C is the speed in meter per second, T is the temperature in Celsius. Now looking at this expression, we can see that C, the temperature of sound in air, is directly proportional to the root of the temperature in Kelvin. Speed of sound in air is directly proportional to the what? Root of the temperature of that air in Kelvin. Oh yeah, you have C is equals to what? K root T. And when you make your case of the formula, K is equals to C over root T. Now using the knowledge of variation proportion in maths, you can see that C1 over root T1 should give you what? C2 over root T2. Now, when you try to play with this formula using mathematical knowledge, so you are going to get this. Root T2 over T1 is equals to C2 over C1. Now, you can use this to solve a question in which they are giving you a temperature of air, the temperature of air, and the corresponding velocity. And they are now asking you that what would that be the velocity at a certain temperature. So you can use this. But in a question where they are not giving you a certain temperature and the velocity of sand, you can use this, and they are just telling you what is the speed of sand at a certain temperature. You can use this formula. So now, looking at this formula, let's just define our terms here. We have where C is the speed of sound measured in meter per second. T is the temperature in Kelvin. This one, make sure you convert your temperature to Kelvin. This one, you don't need to convert to. So let's solve this question. What is the velocity of sound in air at 100 degrees Celsius if the velocity of sound at 0 degrees Celsius is 330 meters per second? Now let's see how to solve this. Now we can easily solve this using the relationship between the velocity of sound in air, or the speed of sound in air, and the temperature. Recall that I've derived an expression for that. So that is what we are going to use very fast to solve this question. Now we are given that the temperature here, so I'm going to use this one as T1. So the temperature that is known here is 0 degrees Celsius. You convert it to Kelvin. So 0 plus 273 Kelvin, that is 273 Kelvin. 0 degrees Celsius is 273 Kelvin. Now, the speed of sound that corresponds to that, according to the question, is C1, which is 330 meters per second. Now, we're given another temperature here at 100 degrees Celsius. So we need to find it in Kelvin, T2. Let's call that one T2. So that will give us 100 plus 273 in Kelvin. So we have 373 Kelvin. So we want to know the velocity that corresponds to this temperature, which is C2, that we don't know. So you recall that we have this formula. Root T2 over T1 is equals to C2 over C1. So make your C2 solve the formula. Just try to rearrange this and make C2 that we are looking for, make it as a subject of the formula. When you do that, you have C2 is equals to what? C1 root of T2 over T1. Or you substitute the value that you're given in the question. So you have C2 will now be what? 330. Oh yeah, come here. It's very simple. 330 is for C1. Okay, put it here. What is T2? This is T2 here. 373. You have it. What is T1? This is 273 for T1. You have it. So when you divide these two guys, 373 divided by 273, the answer that you have gotten, then you find the square root of that answer. So making 330 times 1.167, and you are going to get 385.37. What is the SI unit of speed in per seconds?
Wow, we are able to learn so many things in this video. We're able to learn the meaning of sound wave, how sound wave is being produced by compression and rarefaction. We talked about properties of sound wave, talked about echo and reverberation, how they can be applied. Now, we even talked about some intrinsic properties of sound wave like timbre. We talked about amplitude. We talked about sound quality, and then the measurement of velocity of sound in material medium. Make sure you subscribe to this channel. Click on the notification icon to get notified when I release the next video on wave, so that you will be able to see it. If you're able to learn one or two things, kindly comment what you're able to learn in the comment section. Comment, I beg, comment, like this video, like, comment, share this video. Now I have a question for you. What is that question? What is the SI unit of sound loudness? Comment it in the comment section. And what is the SI unit of sound intensity? All right, see you in the next video. Still blessed. Bye for now.